Hello and welcome to another lecture on time complexity. In this lecture, I am going to show you the intuition behind logarithmic time complexity. Before we dive into a real-world example of an algorithm, let's walk through an example to compute the logarithm base 2 of 16. In this context, logarithmic time complexity refers to a method that determines how many times you can repeatedly divide a given number by 2 before you get to 1. Let's walk through the example to compute the logarithm base 2 of 16. Start with 16 and divide 16 by 2. 16 divided by 2 equals 8. Next, take the result, which is 8, and divide 8 by 2. 8 divided by 2 equals 4. Then take the new result, which is 4, and divide 4 by 2. 4 divided by 2 equals 2. Finally, take the latest result, which is 2, and divide 2 by 2. 2 divided by 2 equals 1. At this point, we have reached 1 and we stop the division process. Let's count the number of divisions we performed. As is observed, we perform 4 divisions in total. Therefore, the logarithm base 2 of 16 is equal to 4. Please note that the boundary condition is equal to 1. Because reaching 1 signifies that the number has been divided down completely, reflecting the logarithm's purpose of measuring how many times a number can be halved until only 1 remains. This marks the completion of the halving process and gives the logarithm's value. Let's explore another example and then find the logarithm base 2 of 10. Again, we want to find how many times we need to divide it by 2, repeatedly taking the largest whole number or floor division of the result until we reach 1. We divide 10 by 2. 10 divided by 2 equals 5. We take 5 as the result, and 5 divided by 2 equals 2 because this is a floor division and we must discard any remainder. And then 2 divided by 2 equals 1. We stop at step 3 because 1 cannot be further divided by 2. The number of divisions is 3. And it represents the base 2 logarithm of 10. Let's take the binary search algorithm as a classic real-world example of an algorithm with logarithmic time complexity. In binary search, we repeatedly divide the search space in half to find a specific target element within a sorted list. Let's walk through the steps. We have an array of 8 elements. The task is to find the element with the value of 2. In the following line, we call the binary search function. Initially, a variable named low refers to the first element at index 0, and high refers to the last element's index, which is the array's length minus 1. Just to recap, the first element in the array has an index of 0, and subsequent elements have incrementing indices. Therefore, the last item of the array is located at the array's length minus 1. The while loop in binary search iteratively cuts the search space in half until the target element is found or the search space becomes empty. In other words, the while loop in binary search keeps searching as long as there's a potential chance of finding the target element within the remaining search space. Inside the loop and in each iteration, the index of the middle element is calculated as mid. Therefore, here, the index of the middle element is calculated by adding low and high and then dividing it by 2. Here, low is equal to 0 and high is equal to 7. Therefore, the middle element is located at index 3. The first step is to check if the middle element matches the target value. The condition is not true. Go to the following line to check if the target value is greater than the middle element. 2 as the target value is not greater than 8. In the last condition, we have concluded that the target element is less than the middle element. In addition, we know binary search operates on sorted arrays. Therefore, we know the target that is less than the middle element must be in the lower half of the array. This is because in an ascending order array, elements to the right of the middle element will always be greater. We know that the target must be in the left half. So the variable representing the high is updated to exclude the right half from the search space for the next iteration. In addition,
We want to get the last element of the left array.
Let's move on to the second iteration. Calculate the new middle element in the following line as we did previously. 0 plus 2 becomes 2, and 2 divided by 2 becomes 1. Therefore, the new middle element is located at index 1 with a value of 3. Compare if the middle element matches the target element. There is no match.
Go to the following line and check if the target is greater than the value of the middle element. Since the target element is not greater than the middle element, we know it must be in the left half of the remaining search space. We can exclude the right elements by updating the high to point to the element before the middle one. This effectively reduces the search space for the next iteration. Finally, in the last iteration, the new middle element will be at index 0. In the first condition, we will check if a match is found here. The middle element matches the target value, and we can confirm that the target has been found. Let's delve deeper into this. In each step, we cut the search space by 2. Initially, we had n, and in the first iteration, n was divided by 2. In the second iteration, we divided the previously halved search space by 2 again. Finally, in the third iteration, the previous result from the second iteration was divided by 2 again. We continued division until reducing n to 1, that is the boundary condition. In each iteration of the binary search, we divide the search space by 2. As a result, after k iterations, the search space has been divided by 2 to the power of k. K represents the number of iterations until reducing the search space to 1. Therefore, here in our example for binary search, we can conclude that the search space has been reduced to 1 after 3 iterations. Rearrange the formula to solve for n and take the logarithm base 2 of both sides. By using the property of logarithms, as is observed above, we can get the final solution. The number of iterations required to reduce n to 1 by repeated division by 2 is log base 2 of n. Logarithmic time complexity is denoted by big O of log n. Logarithmic time complexity is very efficient. As the input size grows significantly, the running time increases very slowly. For instance, increasing the input size from 1 to 1000 only increases the running time from 0 to approximately 10 steps. This makes logarithmic time complexity highly desirable for algorithms dealing with large data sets. I hope you enjoyed learning, and please let me know your thoughts in the comments below. Thanks for watching this video.